We'll be in 4.2 today, which is talking about logarithmic functions. And a lot of times I'll just say log functions just to be shorter, and the log button is what you're going to be seeing on your calculator. So in part 1, we're going to change from log to exponential form, and then vice versa, exponential to log form. Evaluate logs and use basic log properties. And then part 2, we'll do the graphs, finding the domains, and using common and natural logs. So just a review with inverses so it can help us on this lesson. Only one-to-one functions have inverses that are functions. A function f has an inverse function, and we call that f to the negative 1. If there's no horizontal line that intersects the graph of f at more than 1 point. So it has to pass the horizontal line test. Number 2, if a function is one-to-one, its inverse function can be found by interchanging x and y in the function's equation and then solving for y. Number 3, if f of a equals b, then the inverse of b equals a. The domain of f is the range of the inverse, and the range of f is the domain of the inverse. And then number 4, I'll let you read that example there. And number 5, the graph of the inverse is the reflection of the graph of f about the line y equals x, which if you're on a coordinate plane, it's just saying it has a slope of 1, so it's this line that goes, imagine it's straight, not crooked. And then you could always go back to section 2.7 where we talked about inverses. Okay, so if there's no horizontal line that can be drawn that intersects the graph of an exponential function at more than 1 point, and it means there's one-to-one and has an inverse, we're going to start by finding the inverse of an exponential function. So we did do this back in 2.7. Step 1 is to replace f of x with y. So that's where I got that. Then interchange the x and the y, so we switch these around. So now we have x equals b to the y. But if we want to try to solve for y, we don't have a method to do this yet. So to try to isolate this y up here, which is an exponent, we have to use logarithmic notation. So the inverse function of an exponential function with a base of b, so this b right here, is called the logarithmic function with base b. So here's it written out another way for when x is greater than 0 and b is greater than 0, and also the base is not 1. The logarithmic form is y equals log bx, and that is the same as b to the y equals x. So that right here is what we were trying to find on the last slide, and we couldn't have a way to isolate the y with previous methods we've learned. And this is called the logarithmic function with base b. And some uses of logarithmic functions, they help us understand phenomena in the world, such as earthquake intensity, human memory, and pace of life in big cities. So just a few examples of when you will use this. Okay, so we're going to start by changing from logarithmic to exponential form. So you're going to need to memorize this statement here, and that's going to help you a lot on these problems. So I'm using some different colors here. So this is the b, which is located right here. We're trying to turn it into this form. So that means that my b, my base, is a 5. Now if I look at my x, that's right here. So we can just put x over here. And if I look at my y, it's located in the exponent. So this y, this would be the y goes up in the exponent. So 5 squared equals x. That would be the exponential form of this log function. Okay, let's try another one. So if we have the b is still the b, so we'll leave it. Then if my 64 is the x, it's going to go on this side. And my 3 is the y, so it's going to go up here. So b to the third equals 64. Now we're not solving, we're just writing its equivalent exponential form. Okay, this one, here's my b. Here's my x. And my y is going to stay a y on this one. Okay, so that's just converting from logarithmic form to exponential form. Okay, now this one is just an extra example I put in your notes, so if you print it off, you can have another one to look at. Okay, example 2a, changing from exponential this time to logarithmic form. So this time we're going to go in the reverse. Okay, so if I look at this one, I'll go ahead and write our first example. We're going to be doing 12 to the second equals x. Okay, so this time it's starting in the b to the y equals x form. So let's go ahead and let's just start with the y, since we're starting with y equals. Okay, so this would be the y. So we're going to have 2 equals, then we have the log, the b is the base, which is right here. So that's going to go down by the log, and then my x here is going to go on the other side, which is just an x. So we put that behind it. So that would be our logarithmic form for that exponential. Let's go and try another one. B to the third equals 8. I'll start with the y again. So that's this right here. So we'd have 3 equals the log and the b is the little subscript here. So it's just staying as a b. Then our x is whatever's behind the log. So here's our x. Sorry, just an 8, not an equal sign. There we go. So 3 equals log of b with an 8 at the end. Let's try one more. E to the y equals 9. Start with the y. So it's just y equals the log. This is my b. And this is my x. So that's going to go at the end. And again, I put another example in here for you to look at if you would like to print it out. Okay, so now we're going to look at this table here. We're going to use that same formula. And this time we're actually going to evaluate or solve. So we're going to find the actual answer. So the logarithmic expression is saying log 2 16 equals what? So the question you can ask yourself is 2 to what power gives 16? And the way I got that was this 2 is the b, so that's the base right here. Then the exponent is whatever it equals, so we don't know that. That's our y. And then our x is whatever's at the end, which is at the end over here, so that's why we have this right here. That's our x. Okay, so 2 to what power gives 16? So the answer to that is a 4. Because if you did 2 times 2 times 2 times 2, you would get 16. Okay, let's try another one. So if we look at this one, blank to what power gives blank? So our b is the 7. So let me write it out with numbers first. So 7 to what power, because this is our x, so we don't know that, gives 1 to the 49, or 1 over 49. Okay, so we can say log 7 and 1/49 equals, now this one you have to remember, so you probably know that 7 squared is 49. So 7 to the negative 2 is the reciprocal of that. So to get 1/49, that question mark would have had to be a negative 2. Okay, the next one, 25 to what power gives us 5? So you probably know that the square root of 25 is 5. So this is the same as 25 to the 1/2 power equals 5. So that means our missing exponent here is a 1/2. Okay, one more. So this one has some radicals involved. Let's go ahead and use our same strategy. 2 to what power gives the 5th root of 2? So this is similar to the one up above. If the square root is a 1/2, that means a 5th root is an exponent of 1/5. So we're really saying 2 to the 1/5. That is the same as the 5th root of 2. So that means our missing exponent is this 1/5 right here. 2 to the 1/5 would equal the 5th root of 2. Okay, and I went ahead and put 3 more examples for you to go back and look at if you want to print these out. So here's some basic log properties involving the number 1. So log of b equals 1 because 1 is the exponent to which b must be raised to obtain the letter b. So you probably know b to the first equals b. Log b of 1 equals 0 because 0 is the exponent to which b must be raised to obtain 1. b to the 0 equals 1 because anything to the 0 power equals 1. If we look at example 4, it's saying to evaluate or solve. So we just said that this was true. So since these match, we can conclude that this equals 1. If we look at this, remember this is the base, so if you did 8 to the 0, you get 1. So that means our answer here is a 0. And same on this one, if you did 9 to the first, you're going to get the number 9. Okay, now let's talk about the inverse properties of logs. So when b is greater than 0 and b does not equal the number 1, we have these two properties. So you can see the base and the exponents kind of switch spots. Okay, so let's go ahead and solve these two. So we learned this property on the last slide. So we're really just trying to find what's on this other side because this side is in the correct form already. So these are going to be the same. So you just locate the little exponent. So our answer is 5 when we solve that. Now this next one we have to use that other property since we have a base on this one. So again, we're just trying to find what's on this other side here, which is going to match this number right here. So this is going to equal 9. And there's one more example you can look at. So again, you're kind of just matching these up. So if they give you this, this should be the same. And same here, match your x's up. So you should have a 17 on the other side. Okay, that's the end of part 1. We'll do part 2 in the next video.